In this session, we'll be discussing the basics of dust collection system design for woodworking. My name is John Daniel. I lead our corporate efforts in supporting our engineering firms around the world here at Donaldson Company. We also have Amy Miller with us today, who's our training manager. She'll be working behind the scenes and will be moderating the Q&A session at the end.
All right, hello. Thanks everyone for joining us today. As you think of questions throughout the seminar or throughout the webinar, please feel free to just chat them in as you think of them, and we will address them all at a Q&A session at the very end.
We're going to start off today's webinar by reviewing some common woodworking processes where dust collection is usually needed. Then we'll get into the four primary components of dust system design: hoods, ducts, collectors, and fans. We'll finish up at the end with the Q&A session. Please note it can take years of education and experience to become an expert in dust collection system design. The goal of this session is just to give you an overview of the basics. If anybody isn't familiar with Donaldson Company, we've been solving complex filtration challenges for over 100 years. We were founded in 1915 by Frank Donaldson Sr., who invented the world's first filter for a tractor engine. Today, we're one of the largest providers of unique filtration technologies, and we excel at producing high-quality filters and parts. We pride ourselves on having a global reach with a local touch. Our world headquarters is in Bloomington, Minnesota, and we have 55 manufacturing plants and 21 distribution centers around the world. Before I introduce our featured speakers, I want to quickly explain how to engage with us. As Amy mentioned, please chat in questions into the chat box, and we'll be addressing them at the Q&A towards the end of the session. And during the webinar, you may be asked a question or two. You can respond by a thumbs up or thumbs down by clicking the face icon at the bottom of the screen. And with that, I'm pleased to introduce our featured speakers today, Kobe Jenkins and Jason Carey. Kobe's been with Donaldson for over 27 years, including 16 years in manufacturing and 11 years as a sales engineer and territory manager. He currently covers Greater Cincinnati, South Central Ohio, Southern Indiana, Central, and Eastern Kentucky. Kobe studied at Lexington Community College and the University of Kentucky. And Jason resides in Marietta, Georgia. He's a graduate of Georgia Institute of Technology with a Bachelor of Industrial Engineering degree. He's been with Donaldson for 28 years and is currently a regional director in the Southeast Territory. With a family of 4 boys, Jason spent many hours coaching, but with his 2 youngest sons heading off to college this fall, Jason and his wife Susie will soon be figuring out their next hobbies. Take it away, Jason.
Thank you, John. All right, we're glad to be here today. To start off, we'd like to take a quick poll to find out the level of experience for our attendees today. So if you would just kind of chime in there with a A through E there, indicating your experience level from none to experienced.
Well, it looks like we have some A's, some B's, some C's, so it's a pretty wide range. Lots of them coming in. Covering the spectrum, Jason.
Ah, very good. And that's what we like to see, and that kind of helps us as we go through the presentation here. So let's get started. Let's talk a little bit about the dust generated during the woodworking applications and the processes that create them. So there's a lot of important reasons to control dust generated in woodworking, such as improving the overall air quality for the employees, exposure control. We want to minimize any dust in the breathing zones of the operators and other employees in the area. Hood design can play a big role here. There's environmental concerns, which frequently fall under EPA standards. Safety concerns, such as NFPA guidelines. Cleanliness of the facility. In some of our larger applications, we have operations that remove over a tractor trailer full of dust in a day. So you can imagine what that would look like if we just let it pile up. And lastly, there is machine functionality and performance to consider. So there's many different types of woodworking industries, and we typically break these down into 2 main categories: raw materials and finished products. Raw materials include dimensional lumber and rough mill, engineered wood products such as OSB, plywood, MDF, and so forth, and rough sawmills. Whereas finished products are going to include kitchen cabinets, furniture, millwork, and other finished products. The type of raw material is another important consideration in selection and sizing of dust collectors. We break these down into three primary groups: softwoods, hardwoods, and engineered lumber. Softwoods typically have a much higher moisture content, and frequently when working with pine, we would move to like a polypropylene bag as an example of something we might do to compensate for the higher moisture. Hardwoods are used more in finished products like furniture and cabinets, but different species of hardwoods can produce very different dust characteristics, even coming off the same operation. And then there's engineered lumber, which is often used in construction. All right, the map shown here, or diagram shown here, shows several different dust collectors in use. We have our large baghouses kind of shown at the center of the map near the bottom, as well as one outside, near the outside wall in the ship. We see a small cyclone in the upper left corner of the building, and we see an example of an enclosureless collector toward the right-hand side of the map. Now we'll take a look at some common woodworking processes that utilize dust collection. Joining is a flattening of one face and one edge as part of a milling process. Planing is used to smooth and remove excess material from wooden surfaces to create a near finished surface. Both of these processes can produce a large volume of dust and much larger particulate. Most people are quite familiar with sawing and cutting. Now there's many different types of saws. You have circular saws, band saws, table saws, miter saws, and so forth down the line. And many of these saws are hooded in quite different ways. Drilling and boring. Drilling is obviously creating a hole in the wood, whereas boring is removing material around a pre-existing hole. Both of these can be challenging for dust collection due to the depth of the hole being produced and the difficulty in getting the suction to the point where it is needed. Routing, shaping, and molding all involve putting a profile onto a wood component. They can be complicated and automated, or simple like a hand router you might use in your home wood shop. Many of the CNC routers require you to overcome a large amount of static pressure. Lathe turning is the art of shaping wood into cylindrical shapes, such as chair legs and spindles. One of the fun ones we did involving dust collection on a lathe is at Louisville Slugger, where bats are turned on a lathe. An interesting side note regarding Louisville Slugger is that the bats used to be nearly 100% ash, and they are now mostly all maple. This change in species had an impact on the dust collection system. You get far more curls and strands with the maple than you did with the ash. Sanding is a process of taking away material to create an ultimate finished component and then adding finishes like stains or paints. The right-hand picture shows a multi-edge sander. The left-hand picture shows a belt sander. It also shows really poor ductwork. A Donaldson design system would look a lot different, but this is representative of what many shops look like when we first entered them. As you can see in woodworking, there are many processes and machines that create dust. At Donaldson, we break the dust down into three basic categories based on the dust characteristics. These categories will help in our selection and size and style of filtration device. We define Class 1 as light or fine dust, such as dust generated from sanding. Class 2 is a medium size, such as dust generated from saws, routers, and joiners. And 3 would be your larger size dust, such as that generated from planers and lathes. In addition to the size of the dust generated, there are a few other factors that we take into consideration to help select and size a dust collection system. We already spoke briefly about the different wood species and types. Moisture content can be a very important consideration. Are there glues and resins present that can create a challenge? What type of equipment or process is producing the dust? What are the airflow and static requirements of the machine? Is the process continuous or intermittent? How much dust will we be collecting? A 5-gallon pail or a full tractor trailer? What are we going to do with the collected dust? Will we drop it directly into a drum or bag, or will we convey it to a storage hopper? We want to look at the total cost of ownership, and last but certainly not least, we want to consider combustibility. The wood dust generated during the manufacturing process may be, and most likely is, combustible and poses a fire, flash fire, or explosion risk. I'm sure most of you are familiar with the fire triangle shown here. Fuel, oxygen, and a source of ignition produce fire. When the source of fuel, which in our case is the dust we're collecting, is finally dispersed, it can lead to flash fires. When that dust is then contained with a dust collector enclosure, the conditions are right for a dust explosion. We are going to circle back to this towards the end of the session, but it is a complex and complicated topic. Toby, do you want to start talking about system design?
Hey, Jason, thanks. Let's talk about the basics of dust collection systems for woodworking. Here's a diagram of a typical dust collection system. You have a blower or a fan. Creates an airflow which is used to capture dirty air with the hood and then convey the material through a series of ducts to the dust collector. Here the contaminant is separated out as clean air passes through the filter media to the fan where it's discharged to the atmosphere. These systems are some of individual parts that are designed based on the characteristics of the dust and various application factors. If one component's poorly designed, the whole system's affected. In system design, we have two main objectives. We want to accurately predict the volume of air in CFM that's required to effectively capture and control contaminants at their point of generation. We also want to predict the total energy and horsepower required to produce those required airflows. The publication shown here is the Industrial Ventilation Guide. It is an important resource for proper system design. The vent manual is written by the American Conference of Governmental Industrial Hygienists, or the ACGIH. This is a nonprofit scientific organization that advances occupational health and environmental health. They offer multiple courses throughout the year on system design using the Vent Guide as a textbook. I've been to the ventilation conference and attended a couple courses or several courses to develop my design expertise. And we also have a few experts here at Donaldson that are instructors at the conference. If you have any interest in developing your system design knowledge, I would highly recommend both of these resources. The ACGIH guidelines are considered by most in the industry, including OSHA, as the standard for proper ventilation design. There are a lot of different formulas that we use in the design system. The most basic and widely applied is airflow. We refer to it as Q equals B times A. The Q is the total CFM of air needed. In order to get the Q, we multiply the velocity of air, which is the B, by the area of the hood or the duct that the air is flowing through. The formula is one of the basic building blocks in designing dust collection systems. We start with the pickup points and calculate using the formula to get the required airflow at each pickup. This will give us the total CFM needed for the system. This formula is also used when we're calculating the required velocity within the duct. So throughout the design of the system, we'll refer to Q equals B times A over and over and over. The first component that we'll talk about is the hood. This is a critical component for system design that will allow the containment and collection of the dust. A well-designed hood is going to minimize the amount of airflow that's required to effectively capture and control the contaminant where it's released, while minimizing the energy required to do that. When it comes to assessing existing systems, few common mistakes we see are wrong hood style being used, the hood's not located in an effective position, or you have inadequate airflow at the hood. You can see in this picture, the manufacturer provided a hood the full length of the sanding belt, which is great. However, the 90-degree elbow immediately above the hood that you can see in the photo is not ideal. The most common hood style used in woodworking system is a closed capturing hood. It relies on establishing a general flow pattern in the hood opening to produce a capture velocity at a specific distance from the hood. There are four main types of capturing hoods. On the slide, they are in order from least to most efficient and also in order from least to most expensive. So you have a raw edge hood, flanged hood, tapered hood, and then a bell mouth hood. So regardless of the hood style, to be an effective hood, it must be positioned properly relative to the point where the contaminant is emitted. Remember, the first objective in hood design is to minimize the air volume required to maintain capture efficiency. To minimize air volume, the hood must be close to the capture point without disrupting the process. Hoods simply just can't reach out and control contaminants far from the inlet. So think about your vacuum at home. To pick up debris from the floor, the vacuum head must be close to the contaminant or just doesn't have any effect. The hood positioned twice the distance from a contaminant emission point rather than at the capture point will need to draw approximately 4 times more air to produce the same capture efficiency. So the more air means larger equipment, larger ducts, larger fan with higher horsepower, and all of which add increased capital and operational costs. When determining airflow at the hood, the main design factor is called capture velocity, the velocity required at the point where contaminant is generated and gains control of the contaminant and directs it into the hood. For wood dust, capture velocity is typically between 150 to 750 feet per minute, or FPM is what we refer to that, although it's going to depend on the application and the style of hood that you're going to use. So when you're designing hoods, we want to avoid airflow extremes. Too much airflow at the hood or pickup point may mean you're picking up good product rather than just nuisance dust. It also can increase your risk of capturing unwanted particulate like sparks or embers. And since more energy is required to move more airflow, it could lead to higher than expected operational cost. Insufficient airflow at the hood could require additional housekeeping measures to be implemented. Depending on the dust, it may lead to increased risk of exposure. Once we design the proper hood to capture the contaminant, the goal is to move the particulate to the filtration system through a series of ducts.
Sorry to interrupt you, Kobe. Just wanted to remind everybody to chat in your questions as you think of them, and Kobe and Jason will address them towards the end of the session.
Thanks, John. Properly designed duct system should pull the minimum airflow required at each hood, as well as maintain velocities required to transport material through the duct into the collector. And you have to be able to do this utilizing the least amount of energy as possible, minimizing any wear and tear on the duct components. So a few common mistakes that we see when it comes to duct design: incorrect ducting being used, incorrect duct size or fittings being used, and the duct system's just not balanced correctly. The minimum duct velocity is a critical design factor. The lowest velocity, where all contaminant will remain suspended in the airstream, is what we refer to as duct velocity. If you go below this velocity, dust could settle out within the ducts and cause other safety issues. Duct work, no matter the size, must be full of air at the design conveying velocity to avoid any settling out. Here you can see a list of different types of dust and their recommended transport velocities on the slide. For many of the light dust generated in woodworking, like sanding, the industrial ventilation manual lists the minimum velocity is 2,500 to 3,000 feet per minute. However, 4,000 feet per minute duct velocity is for combustible dust, which is typically what will be in woodworking. So you're going to see duct velocities in that 4,000 to 4,500 feet per minute range. If the duct velocity is too high, it's going to require more energy to move the air through the duct. Ultimately can impact the size of the system, as well as create issues such as noise, abrasion, wear and tear on the duct, and other equipment. A few pieces of advice when it comes to duct type. Rectangular duct is commonly used in HVAC applications where you're going to be moving air only. We don't want to use that in industrial applications because dust settles out in the corners. It's okay to use it on the clean air side though. When specifying industrial duct systems, make sure you call out round, heavy-duty industrial duct work. Most dust collection applications will use class 2, 3, or 4 ductwork, which are designed to SMAGNA standards. Typically, the higher duct class rating of the ductwork, the higher the gauge. Spiral duct tends to leak air. It can impact your design airflow by about 10%. And if it's used outside, it also could provide a prime source for water to enter the ductwork and get into your dust collection system. So spiral duct is generally not recommended. Flexible ducts, popular because it allows operators to move the hood locations to fit their process. However, that comes at a price because there isn't smooth inner surface inside the duct. When the air moves through it, it creates a ton of turbulence and therefore requires significantly more energy than traditional hard ducting. So if you're going to use flexible ducting, we recommend minimizing that as much as possible. Speaking of flexible duct, we found this fantastic video showing what not to do. Some flex duct may be required as the machines are moving, but there's way too much in this process. It's going to lead to higher static pressure, lower airflow, which all leads to material buildup in the ductwork. I'm sure it wasn't designed this way, but somebody added flex duct along the way. So if your customer's facility looks like this, give us a call. We can help you. And my last piece of advice about ductwork, avoid T's and 90-degree angles. If your elbows are mitered 90-degree turns, all the air has to slow down, turn, then speed back up. Same with branch fittings. A T fitting creates a ton of turbulence as the air is coming in at a 90-degree angle, and the turbulence equals more energy consumption or a higher static pressure. So if you're designing a system, it's important to select options that minimize the turbulence within the duct and avoid things like T's and mitered 90s. If you're using 90s, we prefer it to be long radius. I mentioned earlier that having an unbalanced system is something that can go wrong with the duct design. When customers add new equipment to an existing system, they often don't consider the impact it has on other existing equipment. So in most cases, existing systems aren't modified to accommodate the additional airflow or static, and it becomes unbalanced. Luckily, if you know the customer is going to be expanding the process, there's a few ways to design future lines into the system so they don't have to sacrifice the performance. Having a balanced system is one of the most important aspects to an effective dust collection system. So it ensures you're pulling the correct amount of air from each hood. A lot of issues have been created in existing systems where the process owner goes and adds additional pickup points, doesn't account for the ramifications downstream. So give us a thumbs up if you ever seen this in your experience. You design a system, you find out later the process owner changed something.
It looks like we're seeing a bunch of both thumbs up and thumbs down, so people are certainly running into this scenario. Bowie?
Sure, I see this quite often. What about you, Jason?
All the time. Yeah. Most of the time, these additions were not planned and the system can become unbalanced. If you know a customer is going to be expanding their process, there are ways to design future lines into a system so they don't have to sacrifice performance. But if a customer needs to add a line to an existing system, call in a professional to help. Don't just do it and expect the system to work. Our next system component is the dust collector itself. The main objective of a dust collector is to filter or remove the dust from the airstream and discharge the collected dust into a container or takeaway system. The objective is to do this as efficiently and economically as possible while operating in a stable and predictable fashion. The most common mistakes or things we could do wrong that we see when it comes to collector design are the wrong filtration technology, like using a cartridge when a baghouse would be more effective, incorrect sizing of a collector, either too aggressive or too conservative, or poor installation or system design, such as poor duct design or inlet orientations. The photo here shows a series of 3 of our RF collectors sitting on a common platform. Over my career, I've used many different dust collector types on woodworking applications. When applied to the appropriate operation, they can all be successful, but put the wrong collector on the wrong application and you can quickly get in trouble. Cartridge collectors, cyclones, and enclosureless collectors all have their place, but baghouses are the most common collectors used in woodworking. Our baghouses are broken down into 3 different cleaning types: low pressure cleaning, medium pressure cleaning, and high pressure cleaning. The high pressure cleaning would be a compressed air system that reverse pulse jets the unit. Enclosureless collectors are limited to no more than 5,000 CFM by NFPA. The RF collector is a workhorse in the woodworking industry. It can handle large air volumes and large volumes of dust. It has a cyclonic inlet that provides some pre-separation prior to reaching the filters. The bags are cleaned with a medium pressure produced by a positive displacement blower, thus saving you on expensive compressed air. The RF also has a single inlet, single outlet, and single dust discharge point. The RF helps with a quick and easy installation due to the fully welded construction. Units are usually lifted off the truck with a crane and set into place. The photo here shows an RF collector. The fan is mounted on the left side of the collector and is connected with the large galvanized duct. You can also see a pulse jet baghouse in the background. The RP collector is very similar to the RF and has a lot of the same features, but the RP uses pleated filter bags rather than the fabric bags over cages. The pleated bags are shorter than fabric bags and they have more square footage of media per filter. The pleated bags can work very well in applications where a high percentage of the dust is sanding fines and applications where there are concerns about interstitial velocity. The picture here shows a modular baghouse. The modular baghouse is has a high pressure cleaning system or pulse jet cleaning system that fires compressed air back through the filters to clean them. The MB comes in square and rectangular configurations and are typically used for low and medium volume applications. Pulse jet baghouses can take up a good bit of real estate, and they can also have multiple inlets, outlets, and dust discharge points. They do, however, typically have lower capital costs than other baghouses. Sometimes a traditional baghouse isn't going to be the best option and we need to use a specialty collector. The Dalomatic G2 is a great selection if we are dealing with agglomerative or sticky dust. These collectors have envelope-shaped bags that have a tremendous snapping action during pulsing, shown in the graphic on the left. The snapping action aids in dislodging the dust cake. The Dalomatic also has a downward airflow pattern, which helps with getting light fine dust down into the hopper and out of the collector. It is a pulse jet collector, so it will use plant compressed air. Baghouse collectors use bag filters. The two main types are fabric and pleated. Fabric bags are installed over metal cages. During filter changeout, the entire bag and cage are removed from the collector. The used fabric bag is removed from the cage and new bag installed in its place. Then the cage with the new bag is put back into the collector. Many baghouses can have several hundred bags, so the process can be very time-consuming and dirty. Pleated bags are a one-piece design. They tend to be shorter in length and take significantly less time to change out. Not all baghouses can use pleated bags, but they are a great option for certain applications. When I'm designing a system, the very last thing that we do after completing all the static and airflow calculations is select and size the fan. Toby, do you want to talk about fan design?
Absolutely. The fan is like the heart of a dust collection system. So it has two job responsibilities. First, a fan must deliver the necessary volumetric flow at the required static pressure to drive the operation of the system. And since many dust collectors can operate with dirty and clean filters, they require airflow. The required airflow is often has to be maintained over a range of static pressures. Secondly, the fan you select should be able to deliver the desired static and airflow with an accurate energy efficiency at an acceptable sound level. So, for example, non-material handling fans located on the clean side of a collector are more efficient than a material handling fan on the dirty side of the collector. Fan challenges generally fall into two categories. It's a poor fan selection or a poor fan installation. A critical component of fan design is static pressure. It's basically resistance that the airflow must overcome due to system components. It's expressed in inches of water gauge. When we design a system, we calculate the total static pressure so that we can size the fan appropriately. Here's an example from a recent system that I designed. We had hoods that totaled of 1.5 inches of water gauge. The ductwork, including straight runs of duct, elbows, branch entries, that all totaled 2.5 inches. The filters in the collector, when dirty, totaled 6 inches. So the total system static pressure for this particular project was around 11 inches. Fans are size based on a system's total static pressure and the required airflow. So let's say I need to size the fan for the example I just gave you. 11 inches of water gauge and the airflow is 9,000 CFM. We use the system static pressure of 11 inches, then line it up with the airflow of 9,000 CFM. Then we line those factors up and we land in between a torque backward inclined, or TBI 25 and TBI 30. So we get we go to the curve to the right where we land. Since it's rare, we land right on the curve. So in this case, I would have selected a TBI 30. To finish things up, and then we'll open up for some questions. There are a few other design considerations that we want to think about. Total cost of the ownership. So some things to consider would be how much energy is required to operate it, where's the unit coming from, how easy is it to get parts, how long do the filters last, how easy is it to change out filters or maintain the system, and what is the life expectancy of the system. Another consideration I want to mention is how technology is being used to monitor dust collection systems. We have smart technology all around us these days, from our TVs to our toasters. Donaldson's developed a device called IQ to make dust collectors smart. This device gathers important process data in real time, creates automated alerts, has historical reports, and it's available to customers at no charge. It's a great way for process owners to manage and track regulatory compliance information and troubleshoot dust collection issues more efficiently. And regulatory considerations, everyone's favorite, right? Each of these agencies must have design expectations to reduce process-related hazards, and as we all know, they aren't always consistent with each other. Knowing the hazards related to the process the system is designed to handle, this will allow you and the customer to make some critical design decisions up front in the process. It can be very expensive and time-consuming to change the design once the equipment is installed and in operation, so you want to try and be out in front of it as much as you can. I want to talk briefly about National Fire Protection Agency, or the NFPA. It's a global self-funded nonprofit organization devoted to eliminating death, injury, property, and economic loss due to fire, electrical, and related hazards. Standards developed by the NFPA are called consensus standards because they're widely recognized by authorities. NFPA standards are referenced in national and international fire and mechanical codes, and they are adopted by many states. The local building inspectors and fire marshals may be required to enforce NFPA standards. OSHA also considers NFPA standards to be good engineering practices, and during general safety inspections may reference NFPA standards when issuing fines to a facility under the general duty clause. Here's a list of the current industry-specific NFPA standards. NFPA 664 provides information to help identify and manage fire, flash fire, and explosion hazards associated with combustible dust and particulate solids found in wood and wood processing industries. Specifically, it addresses the prevention and protection requirements for industrial, commercial, and institutional facilities that process wood or manufacture wood products. This is a recent job we did at a school shop in Wisconsin. This is actually a small cartridge collector. Since the airflow was pretty low at 4,500 CFM, we didn't need a baghouse. We could go with the more economical, smaller size cartridge collector. The dust was combustible, and as part of the mitigation strategy, they went with inlet isolation, high-speed abort gate, an explosion vent, and dust discharge isolation. In the photo, you can see our small DFE collector with the explosion vent on the side where the white rectangle is. You may notice underneath the hopper, we have an NFPA-approved rotary valve, and in the left of the picture in the duct runs, you can see the inlet isolation valve as well as the high-speed abort gate. For those of you that are new to dust collection, just know that combustible dust is important, complicated, and ever-changing. If you have any questions, please reach out. We have combustible dust experts on our team that can help, and that goes for the entire system, not just combustible dust mitigation. Designing dust collection systems for woodworking can be complicated, and there's a lot that goes into it, but that's what we're here for. We've sold countless dust collection systems around the world. We have local support in your market, and we are always here to help.
Thank you. Great job, guys. We're going to finish up with some Q&A. Jason, Kobe, Amy, can you turn your cameras back on now? Just heads up, everyone that attended today will receive an email that includes your professional development hour credit. We're going to put a link in the chat box to our webinar page. Here you can watch on-demand webinars on system design. We'll work on getting this webinar recording available as soon as possible. And there's also a form where you can fill out if you're interested for an in-person lunch and learn or a customized webinar for you and your team. If you have any follow-up questions, you can email. My email address is right here on the screen. Amy, what's our first question?
All right. Can you hear me okay?
Yes.
All right, just making sure. Okay, so here's our first question. I don't see the bell mouth inlet in the field. Why aren't they popular? Like, are there limitations for it?
Well, if you're talking about fabricating it out of steel, it is going to be more expensive, and that's probably why you don't see it there. Where you do kind of see them more often than not, or you do see them sometimes, are all the flex arms that are in plants everywhere. Those typically do have that bell shape to them that helps with capturing more of the dust. But it is just it's a cost thing.
All right, thank you. Second question, what is the advantage of branch location in transition versus main duct? So branch location in transition versus main duct.
So I'm not real sure what they're asking there between the transition and the main duct. What we want to do with those transitions, though, is make sure that when we have an airstream entering, it's at a nice 45 or 30 degree taper. But the main part after that is that the duct changes size. So if we have a 6-inch duct joining a 6-inch duct, it's going to be an 8 or 9-inch duct on the other side of that. So it doesn't really matter if it's further down the line away from the main, but the pieces have to go together where the volume adds up as that additional air is entering the system.
Okay, thank you. Next question, can the system be over-designed to avoid issues if a branch is later added?
Yeah, and that's what we typically, Kobe, did you have something there? I'll let you go.
Oh, go ahead, Jason. That's fine.
Okay.
Go ahead.
Yeah, I mean, most people are going to add processes or equipment later on, so they normally need additional capacity. If we have an idea of where that's going to be, it's pretty easy to design that in. We can leave a branch that's going to go off to the the east side of the building where that future expansion is most likely to be. But yeah, adding that extra capacity is very helpful, but you do kind of need to have some forethought into the design, because if you have all your capacity, as far as the size of the duct or the main itself, where you most likely would tap in is not going to be where the equipment would be located, then it's not as helpful. So it does require a little forethought.
All right, thank you. Next question, what type of damper do you use to balance systems?
Typically, we see just slide gates or blast gates used in the line. Now, we prefer these to be, if for balancing purposes, we prefer them to be higher up where the operator can't adjust them all the time. We want to come in and balance the system, set those blast gates, and leave them in their location, until we have a complete system change. But more often than not, what you see is the blast gates are right down there at the machine, and operators open them, close them, and your system changes constantly.
Thank you. And next question, what are the major watch-outs if you need to install orifice disc for proper balance?
So, I mean, that's just another way. Instead of using a blast gate, someone might put an orifice there to add some restriction in a line so that you're balancing the system somewhere else. Putting that in the line obviously can create some restrictions where you're no longer getting the draw or the suction where you need it in that line. Sometimes those orifices, depending on how they are, can add some noise to the system as well. You get more of a whistling effect through there.
Okay. So here's a question. I think it was you, Jason, that mentioned when you were talking about the RP, you had mentioned that it's a good option for when there are interstitial velocity concerns. So someone's asking, what is interstitial velocity? That's a good question. We probably should have explained what that was.
Yeah, absolutely. So the RF collector is one we showed a picture of several times, the RF and the RP, which is kind of a traditional round baghouse. Well, in these traditional collectors, the tube sheet, which is what separates the clean side from the dirty side, is typically horizontal in the collector where your bags are hanging down. So we talk about two different things there. We talk about a can velocity and an interstitial velocity. The can velocity is that upward draft of air where that dust and airflow are coming up to the tube sheet. And the interstitial velocity would then represent the velocity between those bags. So it's still that upward airflow, but you're kind of removing the bag area. So it's that velocity in between bags. It becomes important with lighter dust. The lighter and finer the dust, the more critical that interstitial or can velocity number becomes. Because if those are really high, it's difficult to get the material to fall out of the collector.
And the reason why you had mentioned with the RP with a specific collector type, I'm assuming is because the bags are spaced out further apart than a traditional baghouse?
Yes, in the RP, which is designed specifically for pleated bags, there is wider spacing in there in general. And then in applications where we really need to lower that, because those RPs have the pleated bags, which have a lot more square footage on them, we can actually remove some bags and plug holes and still have enough filtration area, but you have a much bigger baghouse with fewer filters there. So there are different restrictions or limitations on each baghouses. A lot of times what people are familiar with is an air to cloth ratio, and that is important in a lot of these, but sometimes the limiting factor is more interstitial or can velocity.
All right, thank you, Jason. So next question, I think we kind of addressed this a little bit, but this is asking specific for like school wood shops. So how can blast gates be used in smaller applications like school wood shops to assist in balancing?
Jason, I'll take that one.
Okay.
Blast gates can be used, for example, if you have 6 different machines in your shop and you know that only 3 of them are going to be running at the same time at any point, you can install these blast gates, and when the collector is started up and airflow is set, you basically can use those blast gates to predict how much air that you need for each of those machines.
you.